Yes, welcome to the Maxwell-Boltzmann speed distribution. We have this formula here that we're going to look at. This is as taken from the data booklet, and it's a really useful formula because it basically links between what happens on a microscopic scale, which is the kinetic energy of the particles, or rather the average kinetic energy of the particles, that's what this bar is for, to the macroscopic scale, the temperature of the particles. Notice there's a direct relationship between the average kinetic energy and the temperature of the particles. And we're going to look at that now. Now, if we take any temperature, the number of molecules at different speed varies according to the speed. Let's take the highest temperature, 2000 centigrade. The total number of molecules is basically the area under the graph, and notice there are a large number of particles that have a high speed or a high average kinetic energy. When you look at the one that's 1000 degrees, there's a very strong peak here. The average is going to be somewhere like this, and we have fewer particles that are have high speed. When it's 0 degrees, there are even fewer at high speed. We have this characteristic shape, which is not exactly a normal distribution. It's kind of skewed to the left. So the Maxwell-Boltzmann speed distribution, which is what this is, can be shown graphically as a plot of the number of molecules up on the y-axis against the speed of the molecules. What you notice is that as the temperature increases, the curve broadens out and extends to higher speeds. So basically, the higher the temperature, the higher the average kinetic energy. So here's a high temperature, 2000 degrees. That's where we have a high kinetic energy. This is the equation that we need to refer to. Notice that the average kinetic energy depends on the temperature. Okay. The K is the Boltzmann constant. And here we have it again. This is the temperature. This is the average kinetic energy. The Boltzmann constant is equal to the R, which is universal gas constant, divided by the number of moles. We can write this is equal to 3 over 2. Instead of K, we substitute R over N times the temperature. So this is the universal gas constant. This is the number of moles. And of course we have temperature there. You might see it in this format, so not necessarily the value K, but you might be given R or N or and so on. So the Boltzmann constant is 1.38 times 10 to the minus 23 joules per Kelvin. And there you have it. There's the Boltzmann constant. So as a reminder, this is the temperature. This is the average kinetic energy. This is the universal gas constant. This is the number of moles.